Welcome again. So this is the third part of chapter 9. So here we will start the standard and sizes of the tube and shell. So in this table we can see that the physical dimension of the condenser tube is given in terms of BWG as written over here. Right. So if the tube outer diameter, it can be 3 by 4 inches, it can be 1 inch, it can be 1.25 inches. So for the 3 by 4 inch outer diameter tube, then what is the inner diameter? So for the inner diameter, we take the standard of BWG. So the BWG will define that what will be your inner diameter of the tube. Whereas the outer diameter is 3 by 4 inch, which will remain for certain BW numbers. So for this outer diameter, the BWG is changing from 10 to 18, and during this change we can see that our inner diameter of the tube, so the outer is 19.1 inches and 3 by 4 inches and 19.1 millimeter, whereas the inner diameter corresponding to this 10 BWG is about 12.2 millimeter, and for 18 BWG it is about 16.6 millimeter. So accordingly, depending upon the design requirement, we can choose the appropriate BWG and we can get the inner and outer diameter of the tube. Okay, so what is the effect of BWG? So as the BWG is increasing, the inner diameter is also increasing. That means the tube thickness is reducing because the outer diameter is kept constant. So similarly, if your outer diameter is 1 inch or 1.5 inch something, then accordingly you can take the inner diameter from this table, that for 10 BWG the inner diameter will be 18.6 millimeter. Okay, so this is how we will get the inner diameter when we know that what is our outer diameter and what is our BWG. The next table, this table is showing you that what is the outer diameter, what is the shell diameter standards. So here we have the shell inner diameter, and here we have, these are the different standards for the shell inner diameter. It can be 203.2 mm, it can be 254 mm, it can be 304 mm. So these are the basically these are all shell diameters, inner diameters. And this column is showing you that the shell diameter is in inches, and here it is in millimeter. And this is showing you the number of tubes. So this is corresponding to 1 pass, and this is corresponding to 2 pass, 4 pass, 6 pass, and 8 pass. And these numbers here are showing the number of tubes. These numbers are showing the number of tubes here. So if we choose certain inner diameter of the shell, let's say 387.4 millimeter, which is corresponding to 15 and quarter inches. So if the tube passes are 1, then there will be 91 tubes in the shell. If the tube passes are arranged in such a way that it will make 2 passes, then the number of tubes will be 86. Similarly, if you arrange the tubes in such a way that the number of passes are 4, then the maximum tubes can be 80 tubes. So the number of tubes in the shell will be 80, and so on. So this table indicates that you have the inner diameter of the shell and how many tubes you can accommodate. So remember that what is the tube diameter? The tube diameter, this table is indicating that the tube outer diameter is 1 inch. So the tube outer diameter is 1 inch, and the tubes are placed in the shell in a manner of triangular pitch, and the pitch is 1.25 inches. So we have the shell inner diameter, and we have the tube outer diameter, and we have the pitch of the tube arrangement. So the pitch is 1.25 inches and the arrangement is triangular pitch. And then we can see how many tubes can be accommodated in the shell. So for 1 pass it is 91, for 2 pass it is 86, for 4 pass it is 80. So similarly, for any diameter of the inner shell, we can get the number of tubes. So remember that this entire table is for 1 inch outer diameter and 1 1/4 inch pitch and triangular pitch distribution. Okay. So we have some more tables like these two tables, as you can see. So the shell diameter is changing here also, and the number of passes are changing here also, but this entire table is for 3 by 4 inch outer diameter tube, and the tube pitch is 1 inch and the distribution is square. So you can see that how many number of tubes are accommodated. So for this case, because let's say 13 and quarter, the number of tubes are 97 for one pass, and if it is 2 pass then it is 90, and if it is 4 pass then it is 80, so and so on. So this way we can find out that how many number of tubes it would be corresponding to the shell inner diameter and corresponding to the tube outer diameter, and the distribution of the tubes, whether it is square or triangular, and the pitch of the tubes, whether it is 1 inch or 1.25, 1 1/4 inch, or or 3 by 4 inch. So there are there are different distributions. So 1 1/4, 1 and 1 1/4 inch is given in your textbook. The two pitches are given. Okay, so this is further the same table. So this one is for 3 by 4 inch and 5 by 16 inch triangular pitch, and this is 3 by 4 inch and this is 1 inch triangular pitch distribution. So this is about the shell diameter, tube diameters. As for the inner diameter of the tube, because here given only the outer diameter, the inner diameter of the tube, then we need to go back to this BWG table to find the inner diameter of the tube corresponding to outer diameter. The outer diameter is 3.3 by 4 or 1 inch. Now we will see that some formulation for the shell and tube heat exchanger. So the three common formulas for the heat transfer, that is the rate of heat transfer for the cold fluid, equal to the rate of heat transfer for the warm fluid, and equals to the rate of heat transfer through the heat exchanger, and it is calculated in terms of the overall heat transfer coefficient, area subjected to heat transfer, and delta T. So this is what we learned from the previous chapter, chapter 8. The same thing it will be applied here also, because this is general physical principle, so it is applied to here also. But here there is a change, because the flow in the shell is like this, zigzag, it's making waves, right? So it's not straight, whereas the flow in the tube is straight. So in this case, the flow is neither completely parallel or nor completely counter. So for that reason, when you calculate the delta T, which is log mean temperature difference, it should be multiplied by correction factor F. So the log mean temperature, when you multiply it by correction factor F, then it gives you the delta T, and this delta T will be used here to find out the rate of heat transfer. So LMTD, we will always calculate for the counter flow in this case, and then we will multiply it by F to find out the delta T to substitute in the expression of rate of heat transfer. So what is this correction factor and how do we calculate this? So this correction factor F has a long expression, and that comes from the experimental correlation that the correction factor F comes out to be in terms of R and S. Then what is R and what is S? So the S can be defined by this way, and R is your capacitance ratio, that is MCPC and M dot W and CPW, which means that the capacitance of cold fluid divided by the capacitance of our warm fluid. So you calculate S and R first, and then you can calculate the correction factor F, and then you substitute here to calculate the delta T, and then you can calculate the rate of heat transfer. Okay, so we have the equations to calculate the correction factor in terms of R and S, and now we can see that there is a graph, there is a chart. So from this also we can calculate the correction factor F. in terms of R and in terms of S. So we need to know what is R and what is S, and then we can calculate the correction factor F. So remember here that this correction factor, this chart or this graph is applicable for one shell and two or more passes. So it's like one shell 2 passes, or one shell 4 passes, or one shell 6 passes, 8 passes, like that. And this chart is again for the correction factor, and this is for 2-4 shell and tube heat exchanger. So what does this mean, 2-4? 2 2-4 means that 2 is the number of so the 2 is indicating the number of shells, and 4 is indicating the number of passes. So the 2 shell 4 passes here, and here it is 1 shell 2 passes or more passes. So we saw that the overall heat transfer, or the rate of heat transfer, can be calculated in terms of the overall heat transfer coefficient, in terms of the A naught, that is the area subjected to heat transfer, correction factor, and the log mean temperature difference. So remember that this log mean temperature difference is always for counterflow when we deal with shell and tube heat exchanger. So the overall heat transfer coefficient again will be calculated the same way, that you need to calculate the inner side heat transfer coefficient, and you need to calculate the outer side heat transfer coefficient, and then you need to do this multiplication to find out the tube side heat transfer coefficient. From inner surface to outer surface you have to make it, and then you can calculate the overall heat transfer coefficient. So if we want to take into account the falling resistance, then we can use this expression to take into account the falling resistance. Okay. So here this is again the repetition, that the same plot is presented here, that we need to calculate the correction factor, and it can be taken from the chart with when you have the given value for R and S, and this is applicable for one shell and any number of passes in the multiple of 2, like 2, 4, 6, 8, and so on. Now comes to the pressure drop. So as far the tube side pressure drop is concerned, then in the shell, the tube, the flow in the tube is entering into the shell and then going into the tube, and if it is one pass, then it is going out from here. If it is one pass, if it is two pass, then the tube is the fluid is going into the tube and then coming back, and it is leaving like this. Okay, so what is involved here? The two losses. One is the minor losses when the fluid is entering and leaving, and the one is the friction losses when the fluid is traveling in the tube. So when the fluid is traveling in the tube and it is one pass, then only one length is considered, and when it is two pass, then the length is multiplied by the number of passes, because the flow path is doubled. So the flow path is multiplied by the number of passes. So when we calculate the pressure drop for the tube side, then the number of passes is multiplied by the L to calculate the length of flow path, and the rest of the expression is same common expression that we use for the pressure drop, that is F multiplied by L divided by D multiplied by rho divided by 2 multiplied by V square, which is very common expression for the flow in a pipe or flow in a tube. Calculate the friction losses. As for the minor losses for the inlet and outlet plenum and for this band, so for the minor losses we call it the return losses, return header losses. So this can be calculated as 4np multiplied by 1 by 2 rho V square. So 4np is your minor loss coefficient. If the number of passes is 1, then the 4 is the minor loss coefficient, and it is multiplied by np as the number of passes increasing or decreasing. So the total pressure for the tube side can be written in this way: the tube side pressure drop plus that pressure drop in the return header, and then it can be written in this form. So here one thing need to be remembered, that when we calculate the heat transfer coefficient for the tube side, and which is basically the HI, So this heat transfer coefficient, tube side heat transfer coefficient, will always be calculated as in the case of double pipe heat exchanger. So as for the calculation for the heat transfer coefficient is concerned, there is no difference in double pipe heat exchanger and shell and tube heat exchanger. Similarly, as for the friction losses in the is considered, there is no difference in the double pipe heat exchanger and shell and tube heat exchanger. Okay, so now comes to the shell side. What is the heat transfer coefficient for the shell side and what is the pressure drop for the shell side? Okay, for heat transfer coefficient for the shell side, we need to calculate the equivalent diameter. So what is equivalent diameter? Which is 4 times the cross section area and divided by the heat transfer perimeter. So there is this shell, there is a big shell, and inside the big shell the tubes are distributed in a square pattern. So when the tubes are distributed, either it is a square or triangular fashion. So if it is distributed in a square fashion, then we will just take 1 unit of square. So this is 1 unit of the square distribution of the tube. So out of this 1 unit, so what is the cross section of the flow? The cross section of the flow is that this is the square, because this is also pitch and this is also pitch. So PT square is the cross section of this whole square. PT square, this term here. And then the whole square is not available for the fluid flow because some of the space is occupied by these tubes. So quarter here, quarter here, quarter here, quarter here. So the one circular space, one circle equal to the one circle is occupied by the tube. So we need to subtract the area of the circle from this PT square, so which is this. So now it is 4 times the cross section area available for the flow. Okay, and then is heat transfer perimeter. So what is the heat transfer perimeter? The heat transfer perimeter is this outer surface perimeter of the tube, so which is here and here and here. So the quarter perimeter here, quarter perimeter here. So 4 quarter means the one circle perimeter, and this is what the perimeter. So this is how we calculate the D equivalent for the shell and tube heat exchanger for the shell side basically. So if it is a square tube distribution, if it is a triangular tube distribution, then the same can be achieved, and which is this expression. Okay, so once we have this D equivalent, we can calculate the Reynolds number for the shell side. So what do we need to find out the Reynolds number for the shell side? We need to know the velocity. So how do we calculate the velocity? Like if we have the mass flow rate, then we can divide it by density and divide by the area of flow. So we can have the velocity for the shell side. Okay, so how do we calculate the area of flow for the shell side? So remember that if you see in this schematic, the shell side fluid is going up here. So this space is acting as a channel for this flow, and then it is moving here, and then it is going down, and then it is moving here, and then it is going up and down, right? So we can consider, we can approximate that the fluid in the shell and tube is passing through the tubes is like this, is passing through the tubes like this from top to bottom, and there are baffle spacing, and then it is going like this. Okay, so if we consider the 1 unit, so in this 1 unit we are considering that the fluid is passing through this way. So when the fluid is passing through this way, then in the space it has tubes across this, so it will face the tubes perpendicular. So the sum of the, so what is the cross section? If you cut the shell from the middle, then you see that this dimension is ds, which is basically the inner diameter of the shell, and this distance we call it spacing between the two baffle spacing, which is b. So we will get this rectangle. So the one dimension is ds, another dimension is b. So if you multiply b and ds, then you will get the total area. But total area is not available for the flow because there are tubes which are occupying certain space. So how much, what is the ratio of the the area which is free from the tubes and what is the total. So if we consider the pitch like this here in this example, that the flow is striking from the here, so this is the passage for the flow, and some of the space is occupied by the tube. So if you have a space of one pitch, out of the one pitch the only available space for the fluid is this C. So this space only is available here out of the PT. So the ratio of the area is C over PT. So out of the PT only C is available. So we need to multiply this ds and B by the ratio of C over PT to find out that what is the actual area available for the flow. So this we call the flow area AS. And once you know the flow area AS, we can find the velocity Vs. So this is the velocity in the shell side, and once we have these things we can calculate the Reynolds number for the shell side. Okay, so after having the Reynolds number for the shell side, we can find the Nusselt number using the correlation for the shell and tube heat exchanger. Remember that the correlation for the Nusselt number for shell and tube heat exchanger is different than the double pipe heat exchanger expressions. So here we have that is 0.36 multiplied by Re raised to the power 0.55 and Prandtl number raised to the power 1 by 3. And this expression is applicable for a wide range of Reynolds number, that is Reynolds number greater than 2000 and less than 1 million. So it's a very broad range for this applicable. Okay, so once you have the Nusselt number, and then the other thing you can calculate the heat transfer coefficient and overall heat transfer coefficient in the same way as the double pipe heat exchanger expressions are. Okay, so here we are done with the Nusselt number and heat transfer coefficient and overall heat transfer coefficient. Now how can we calculate the pressure drop for the shell side? The tube side we already covered. So for the shell side we need to see what is the flow path. So if we see here, what is the flow path? So the fluid is going up and then traveling and then going down and then traveling and then going up and then traveling and then going down and so on. This is so if we consider that what is the total length of flow for the fluid, then it is traveling one diameter here and then 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 one diameter here. So how many diameters? So 1 2 3 4 5 diameters it is traveling. So the length of the flow path will be the diameter ds multiplied by the length of the heat exchanger. Okay, so here it is, but how much is the length? So the length is equal to 5 times the diameter. So this ds must be multiplied by the 5 in this case. But this length, this turning can be less than 5, it can be more than 5. So it depends upon the baffles, how many baffles you have. So how many baffles we have here? This is one baffle, this is second baffle, this is third baffle, and this is fourth baffle. So the number of flow paths or the number of turns in the flow path is one more than the number of baffles. So if your number of baffles are 4, then the ds must be multiplied by number of baffles plus 1. Okay, so that will be the length of the flow path. Okay, now coming back to the pressure drop expression for the shell side. So this number of baffles plus 1. So what does this indicate? This indicates the multiplying factor in the value of ds. So this together will give you the length of the flow path. So this is your friction length. So the friction length multiplied by the dE and multiplied by the friction factor and multiplied by rho v square divided by 2. So this will give you the pressure drop for the shell side. Okay, Then how do we calculate the density is given V as a shell side velocity. We already discussed that. So only thing is that friction factor we did not discuss. So how do we calculate this? So remember that the shell side, the flow path is not straight and not smooth. So we cannot use the conventional friction factor formula like what we have for turbulent flow in chapter 5 and 6. So we cannot use that. So here we have a different correlation for friction factor. Uh, so it depends upon the shell side Reynolds number, and this is the friction factor correlation that is applicable for the shell and tube heat exchanger for the shell side, and this is applicable again for a very wide range, like from starting from 400 to 1 million. So we can calculate the friction factor using this formula. Okay, so what is next? So after calculating the So now we know that how do we calculate the pressure drop and how do we calculate the heat transfer coefficient and overall heat transfer coefficient for shell and tube heat exchanger. Now it comes that how do we calculate the outlet temperatures. So we know that from the double pipe heat exchanger that we have two methods for calculating the outlet temperature. So the one is LMTD method and another is ENTU method. As for the LMTD method, so here this is how we calculate the final temperature of the fluids. So we are using these temperature expressions here without derivation, because the derivation we have seen in double pipe heat exchanger, so we are not doing it here. So this is the final temperature expression. So if you know the value of S and R, which are two parameters, so the R is the capacitance ratio, we discussed it several times, and S is the new thing here. So what is S? The S is the parameter, and we define this parameter in this way: S equals to 2 multiplied by 1 minus C1 divided by C2 minus C1 and C3, and C1, C2, C3 are defined here in this way. So to find S, we need to use this expression, and the other way is that you can use the chart and you can find the value of S from this chart. So you need to know UAMCPC and the value of R, and once you have these two values, you can look the value in the chart and find what is your S. So there are two ways: one that you can use the formula for S, and another you can use the chart for S. And this is the bigger picture of the chart for S, that S, you need to know what is your R and you need to know what is your UA MCPC to find out the value of S from this chart. Okay, so second method is ENTU method. So in this method, again we can calculate the final temperatures T2 and T2, and here we know that the ENTU method is always depending upon this capacitance condition. So if the cold fluid capacitance is less than the warm fluid, then we will use this set of expression, and if it is vice versa, then we will use this set of expression. But in any set, what we need to know is E and C, and what is E and what is C. So the value of E can be calculated by this expression, and it's a long expression, again come out from the derivation, so we are not showing that here. And then the C is this capacitance ratio, that is M minimum capacitance over the maximum capacitance. Okay, so when we want to calculate the E, what do we need? We need C and N. So C we already have here by this, and what is N? The number of transfer unit. So the number of transfer unit we will calculate by using this expression, UA over MCP min. So this way we can calculate the final temperatures by using the ENTU method. So here again that we have two ways of finding the E. Either you can use this long expression for calculating E, or you can go to the chart, and then you need to know what is the N value and what is C value. So the corresponding to N and C, you can find the effectiveness. So there are different chart, and this chart is applicable for one shell and two passes. One shell and two passes. and any multiple of 2 tube passes. So that means one shell 2 pass, one shell 4 pass, one shell 6, 8, and so on. Multiple of 2 passes, multiple of 2, any number of passes, but multiple of 2, but the shell always remain 1. So you need to know C and N to find out the effectiveness in this case. So we have another chart, and this chart is again for effectiveness. When you know that what is your value of C, so these are the value of C, and this is the number of transfer unit N. So based on the C and N, you can choose the combination and you can find what is your effectiveness. But remember here that this is applicable for 2 shell type of shell and tube heat exchanger. So any multiple of 4 tube passes, like 4 passes, 8 passes, 12 passes, and 16 passes, but the number of shell is always 2. So this is about how we calculate the final temperatures using ENTU method. So this is all about the fundamentals and the theory of design and analysis of shell and tube heat exchangers. So there will be a little bit more when we solve the problems, but this is like most of the theory is covered here. And then there are some constraints. Then when we solve the problems, then directly we will discuss about the constraint. So the theory part is complete in these 3 videos. So hope that you understand this, and then in the next video we will see that some tutorial problems. Okay, thank you for your understanding.